All right, so we're going to talk about some mechanisms for generating these power law size distributions. And the way we're going to do this is we're going to talk about some very, very sort of basic elementary ones which have some nice ingredients in them. So randomness, just a really crucial thing to acknowledge in any system and to appreciate and to try to model and understand in the history of the universe. Randomness has played a very big part. All right, so we're going to have randomness in there. So it'll be random walks. We'll look at that. Really nice problem. We'll see how that can inform us about ways in which power laws can fit together. So it's called scaling relations. And that will pop up. Naturally, when we start to think about things like borders of systems that are random in some way. All right, we'll get to that. It's going to be river networks. And then we'll talk about transformation of variables. So again, a very kind of elementary thing where we can take nice, easy to understand distributions, exponentials, Gaussians, and so on, and see how a simple transformation of variables will lead to a power law size distribution. All right. Now, that's this section, and from there we're going to move on to much more kind of deeper stories, dynamic ones for how things become things, and we'll see some really fantastic work, which applies to all sorts of systems. All right. So here are the production company, Lamy and Celia. All right. So as I said, random walks will be first. And then we'll get into variable transformation. Good. Yeah, Doctor Who will appear. Little TARDIS action. All right. So as I said, why complexify? It's a fantastic problem that we still don't quite understand. And we have the Big Bang. That's a big deal. We kind of think that's where things started, and there's a lot of work to be done there. And obviously, but then once we get this big soup of stuff and some stars form and all these things, and we can probably start to understand that quite well, we have to eventually confront the issue that life has begun. We have what I like to think of the advent of algorithms is life, right? So life begins, takes off. We have all sorts of games being played out, and algorithms are really the story there. And complexification is the result. So randomness is a big deal. So we have randomness in there. Certainly if you think about one of the great mechanisms of complexification evolution, which we have a basic understanding of in terms of random mutation, but there are all sorts of other things that are coming out now with epigenetics. So randomness is at play all the time, and we'll look at a very, very simple one, as I said. So it's going to be random walks, really pure randomness, flipping coins. So here it is, the most basic one. So we're going to have one spatial dimension and, of course, one time dimension. We're going to make it even simpler for ourselves by making time and space discrete. All right, so space is cut up into 1, 2, 3, 4, and then 0, -1, -2, -3. And we're going to have a little random walker. So someone, if you like, in the classic way of presenting this problem, who's not feeling so good, right? They've had a lovely time at the pub with their friends, and they are now not so good, and their friends are not helping them get home. So this is bad. They start wandering off in all sorts of directions, and they're so bad that they, as they move from point to point, then they just randomly choose which direction to go in. So we're a bit worried about our friend here. We should be, because they've set off. So will we ever see them again is a good question. Well, that will be the kind of game we'll focus on. All right, but let's understand random walks a little more first. And they're really surprisingly complicated. You wouldn't think a power law size distribution would pop out of random walks, but okay. But there are much more elementary things to get through first. So, all right, so the step, we'll call it epsilon sub t, the step at time t, is going to be plus or minus 1, right? So it's going to shift 1 or minus 1 in space with probably a half, right? And so we can generalize this by making it p and 1 minus p if we have a weighted coin. That's good fun. couple of examples. All right, so 4 examples on this page. So a couple of couples. So this is just this is the sum of these plus or minus ones being carried out, right? So at any time step, it doesn't matter where our drunk is, right? So their position is x, and so there are 10,000 time steps here. So we're flipping a coin, right? If we get heads, we'll call it a +1. Tails, we call it a -1. And so you see this wandering around. Say in the top one, you see that this drunk comes back to the pub, right? So the random walk comes back to the pub. You can see there's some crossings back to returns, if you like, to the pub. So we'll call them returns to the origin. And then eventually, though, after about 5,000 steps, does not make it back. So it's wandering around, right? Not doing too well. You see in the bottom example, there's some returning to the pub, but then eventually wandering away with some chance still of returning, but we're going to figure out what that is. They look like they're not going too far, but that's a long time to spend away. So there are some very peculiar things, and so let's talk about that. All right, so simple things. So a little bit of math, very simple. So the displacement after t time steps. Simply we're adding up these pluses and minus ones, right? Plus ones and minus ones. And so the expected displacement is in fact 0, right? So we take the average of this sum, and then you're allowed to take the sum of the average. The average of each plus or minus 1 with probably over half each way is 0. So we get the sum of zeros. So we expect them, our fellow who's not our intoxicated friend, to be actually back at the pub. Like, so if we just step out and look, where's Fred? We expect them to be right there, if we're very oddly statistically minded. Now this doesn't work if they've taken an odd number of steps. Okay, that's true. But we expect them to be very, very close, right? Plus or minus 1 away. So, so we would think that right, so time is going on, so we would think the chance that they should drift away, although there's no bias in here, but we just feels with this randomness that they should move away. Well, let's see. So very important thing about random walks, and this appears in all sorts of other kind of more complicated problems, is the variance, right, the spread. So, and you'll have a nice problem in your problem set about this. So, okay, so simplest thing, so we'll look at the variance of this variable x of t, which is the sum of the epsilons, right? So just put that straight in. And variance of a sum, they're all independent, so this is the sum of the variances. That's a nice property of independent variables. The variance of each one of these, you can calculate it easily. It's 1, right? So there's a half times minus 1 squared plus a half times 1 squared, which is really a half plus a half, with 1. So it's t. So the variance is t. All right. So that's one of the nice properties of the variance, which is a bit of a funny thing in some ways, but it has some nice mathematical properties. All right. So the variance is t. So that means that the typical displacement, the standard deviation, is the square root of the variance, is square root of t. So we're actually seeing, on average, if we had a whole bunch of drunks go out, and we'll come back to ball bearings, might be a more savory choice, but if they're all wandering and they're not bumping into each other, then we expect to see them spread out, actually, right? So on average, all of them should be back at the origin, but they're spreading out. Okay, so that's a very simple kind of scaling law that's popping out. We'll come to this kind of scaling later on in the course when we talk about allometric scaling and these kind of big system level type scalings. We're really interested in the statistical distributions mostly at the moment, but this pops out as well. All right, so let's call it additive aggregation or accumulation. We'll have some variations on that concept as we go through, but that's what this is. It's incredibly simple, right? Independent, just adding these plus or minus ones up, but we get out a square root of t. All right, let's see if this thing will work for us. Okay, so I'm just going to run this for a couple of minutes, believing that I can control YouTube. And before I do that, I want to show you, so this is going to be a little bit about the stock market. This is sometimes called a bean machine. Galton, Sir Francis Galton, who's a bit of a funny character, but he did all sorts of things. So this is another word in here, quincunx. So there's a link there, and if you so for instance, so it's just a fun little thing, right? You've probably seen this, but this is all of these guys are doing little random walks, right? They're bouncing with probably a half one way or the other, and so this is very nicely going to go down, and we're going to count how many times we get a ball bearing after. So this is 18 steps, ending in these various locations. So the variance here, I guess you can see that the variance here is t. So this the typical width of this distribution will grow like square root of t. So time here is the number of rows, right? So you can imagine space is going across. This is time. So it looks like, of course, there sort of are two spatial dimension things, but we can think of time as going down, space going this way, and we get a very, very special kind of distribution comes out. It's the Gaussian. It's a very famous way of producing it through kind of a combinatorial thing. Of course, it's approximate, but it's a in the end, in the limit of large n, large time, and enough ball bearings, you will get a normal distribution. So that's a nice calculation, right? It's a nice little counting calculation. Now I have another one that's been running for a bit longer, and you can see it's starting. It's not perfectly symmetric. Maybe there's something wrong with the random number generator, but it's okay. There's sort of a few more in the middle here, and then it falls away. And in fact, there've been none out here. So these are very unlikely, right? We've talked about this with power law size distributions empirically, right? Really, really unlikely. So square root of 18 is sort of an estimate of the typical width here, but it's growing like root t. So not very wide, right? And you really don't get 10 sigma stuff, right? You don't get 5, 6, 7 sigma stuff, but you do with power law size distributions, which we're all thrilled about because we're physicists. And we love our power law size distributions. Okay. Eventually we'll see that they're not all power law size distributions, but it's fun to pretend that's true. Okay, so maybe we can come back to that guy later on. So these ones are just drooping down. You can see, yeah, it's going to take a while. This was a real outlier here, right? There's one of them there, and in fact, well, there've been one each now, but that's after 2000. Okay, great. All right, so we're going to listen to some a couple of minutes here about the stock market. Please work. Thing works.
So here's Francis, the latest probability machine at IFA. And what we have here is the red bars representing index portfolio 100. And it shows the last 50 years of monthly returns. So 600 months of accumulated data, and it's put into a histogram representing the unusual events in the four tails, both high and low, and the most common average returns in the center. What you're seeing is this physical device that randomly drops these beads through these pins. Every time a bead hits a pin, it has a 50-50 chance of going left or right. And amazingly, after these 5,000 or 6,000 beads fall, they end up forming a distribution that is very similar to that of portfolio 100, index portfolio 100. Now these beads are brought from the bottom of this in a little reservoir. A little cup of beads are brought up this chain through this point, dumped into this little reservoir where they bounce around, fall through the pins, and drop into various channels that end up looking very much like the actual returns of portfolios.
All right, so that's somewhat ridiculous, but stock market, there's more we could talk about the stock market being modeled by machines and so on. Some nice work in Terry Pratchett, if you're familiar with that kind of material. All right, so I do apologize because I think it feels like there was Comic Sans involved in this one. But anyway, generally speaking, not beautiful. Okay, so this one's fun. Let's try this one too. Some great moments in televised random walks.
The last one in $10,000. Now he gets that over. He gets that one over. That has never happened before, incidentally. That was an historic moment on The Price is Right.
So that was kind of crazy. Let me boldly try this
Last
again.
one in $10,000.
There you go. I mean, who knows how well it works with the half-half, but boom.
Now he gets that over. He gets that one over. That has never happened before.
Great moments. All right, great moments.
Historic moment on The Price is Right.
But there you go. Sitting right there is a random walk, and they've got the nasty little zeros on the side. So they know what they're doing. Yeah. Now, on the other hand, of course, we've just said that we expect, on average, that it will end up in the middle. So, of course, that's going to be less and less as we get a bigger. But that's on average. On average, you should win that. Not going to happen. All right, so let's see. All right, so what I said was a little rough, but yeah. So on average, we expect it to be in the middle. You can compute, if you like, the expected return from Plinko. We're not going to do that. All right, so let's count some random walks. We have to think about this a little bit, and we'll see where this goes. All right, so we're going to get a nice. We'd like to see what that distribution is. I've said it's the Gaussian, but let's see if we can figure out how to do that. So we've had a length. We've had t flips of our coins, and each specific random walk, right? Any one of these random walks, like if you look at the exact details of it, right, it was a +1 and then a -1 and then a +1, right? The exact sequence. The probability that appears is 1/2 to the t, right? Because it's a very, it's all each choice that was made in that path has a chance 1/2. Now, that's good. It's a very important thing to remember. So each specific trajectory is equally likely as any other trajectory. But the ones that end up in the same place, all right, so that's different. Okay, so we want to think about, if we're getting this distribution, all the ones that end up in the middle, they've all come from different, in principle, they can come from different paths. You'll have them repeating and so on with those machines, but we'll count up all the different ways of getting there. So, right, there's a very natural way where we flip between counting and probability. It is hot in here. I don't know if you've noticed, but it is hot in here. So let's use some these math things to get ourselves there. So we're going to define n, and this will be a function of I, j, and t. So we're going to have t steps, and we're going to start at x equals I and end at x equals j, right? So it's a very general expression. If we put in 0, of course, x equals 0, that means we've started off at the origin and taken t time steps. But let's imagine we've started somewhere, and this will be helpful. So if we end up at j, then we have to have moved, overall, we have to displace, our random walker has to have displaced by j minus I, right? Plus j minus I steps, right? So j could be negative, I could be, right? This whole thing could be a negative quantity, but this is, so I plus this quantity gives us j. So then I have a question for you to figure out exactly how many different steps there are that do that. It will depend if it's even or odd, so we'll clarify that a little bit. So for instance, the number of ways to return to the origin after an odd number of steps is always 0, right? So you simply can't do it. So after an even number of steps, you must be either at 0, plus or minus 2, plus or minus 4, plus or and after an odd number, you must be at plus or minus 1, plus or minus 3. So that's just a funny little piece there. But actually, I wonder how long Plinko is. Interesting. So, all right, so it has to be odd, yeah. Right, okay. Ends with an odd number. Fine. So, so you have to figure that out. Well, it's not bad. So it's a binomial. It's t choose, this quantity on the bottom, t plus j minus I over 2. So that has to be an even number on the bottom, the t plus j minus I quantity. All right, so fine. You'll get that done. We can talk about it later on. So what's the probability that we get to x of t, this position x, after t time steps? And as I said, we need to either think about odd or even. We'll think about even numbers. That's going to help us. And so after 2n time steps, we're going to be at position 0, plus or minus 2, plus or minus 4. The most we could, if we've had all of our n choices been, all of our t choices have been plus 1, we'll end up at 2n. If they're all minus 1, we'll end up at minus 2n. So that's the limit, right? That's as far as we can get. So we've traveled out. Very, very unlikely. Okay. So we know it's even. This x at t, after t time steps, after 2n time steps. So we'll say it's equal to 2k. It'll help us a little bit. And with this expression, which you've so very nicely figured out in your assignments, so we can just plug things in. So we have I equals 0, j equals 2k, right? So we're displaced to 2k, and t equals 2n. So if we go back, right, so we're going to have a 2n in here, 2n, yes, all right. This will be a 2n. There's a 2n plus 2k minus 0, and so that should be our business. Yep, good. Right, so we end up with 2n, and there was a 2n plus 2k divided by 2, so it ends up as n plus k. All right. So that is the probability distribution, right? We've got it. It's proportional to this. We have to normalize it. It's not too hard. We have to think a little bit about that. But it's proportional to 2n over n plus k, right? So on the previous page we had the number of paths. Probability will then be number divided by the total number possible. So we have it. It's a binomial. So we have to actually deal with binomials. That will involve Stirling's approximation and show how this guy, right, 2n plus k, ends up as this guy. So somehow binomials pop out a root pi. The glorious thing in here will be Stirling's approximation. Magnificent thing. So we're going to get gamma functions, factorials. Really, really nice. Okay, so and that will pop up again when we look at Herbert Simon's model for rich gets richer. Just a great thing. Just a great thing. All right, so the whole is different from the parts, right? They're all little plus or minus ones. There's nothing, there's nothing about a normal distribution there, but we've combined them in a certain way where we get out this fantastic thing, the normal distribution. More generally, and this connects into our power law size distributions. Okay, and that's an assignment question, just to be clear. You have to work on this to get that out. Okay, so stable distributions is a link to the Wikipedia page. Fella, where's Fella? I must have Fella sitting here. Oh yeah, right. Volume 2, great, just great stuff. Really fun book. Probably not for everyone, but if you really get into stable distributions, you may enjoy this. Of course, this is I had this before this thing called the Wikipedia existed, and the web was around. Okay, so stable distributions. So they're a generalization of the Gaussian, right? So one of the very nice properties of the Gaussian is if you add two variables that are normally distributed, you get another one that's normally distributed. right? The variances add, the means add, and the whole thing is normally distributed with that mean and that variance. Now, it turns out there is a whole, so it's what you would call stable under convolution, because the process of computing the new distribution is a convolution. I'm adding some more here. So it's stable. The form of the distribution is stable under convolution, right? The parameters change, but it's stable under convolution. So there's actually a whole range of these guys. The Laplace distribution, which instead of having, so e to the minus x squared is normal distributions follow out incredibly quickly. The Laplace decays as x to the minus 1. If x is our variable here, and it's actually about 0. There's also, say, the inverse Gaussian, which is x to the minus 3 halves. There's a bunch of others. Really nice stuff. And all of those are stable under convolution. Now, it feels like you might get that's speaking sort of a mechanism for creating these mysterious power law size distributions. It's plausible that happens. But we'll say that there are more elementary kinds of mechanisms that, in the same way that we went from this plus or minus 1 random flip, which is just a really nice, simple process, to this rather remarkable mathematical structure, the Gaussian, we'll see that much more simple ingredients can give us these power law size distributions. So it's nice, it's beautiful stuff. Should you get carried away with it? Maybe, I don't know. Really great, all sorts of things. Renormalization, group theory, really fun. All right, so it's a kind of universality, right? It's just a random shout out to Princess Bride. I don't know. I can't tell you that it's good. So there's plus or minus root t. If I got that right, I think so. Okay, so maybe there's but so 95% confidence interval is sort of being described roughly by the standard, standard error there. And so we're building, so here's one example random walk, but if we look at all of our random walks and we make our little histogram for them at each time step, and we send out bazillions of them, then they start to fill in a nice normal distribution. And as time goes out, we see that distribution widens, and it becomes a better and better bell curve. All right, so this is diffusion, right? So this is diffusion. We're going to talk about spreading, contagion on networks and in other ways later on, because it's one of the fundamental processes of the universe, if you like. Basically, it's really how things spread. Incredibly important. But this is the most simple physical mechanism for spreading. It's diffusion. Things, if you just have a sandpile, right, and it starts to spread out through erosion and so on, diffusion is smooth things out, right? So, unfortunately, our big story is that the whole universe is diffusing in some way due to the second law of thermodynamics, quite against what we see, which is complexification. But we have this idea that we'll all end up in a big soup. All right. We don't have to worry about that just yet. Let's see. So, again, it's a random additive growth mechanism, right? So there's a sense of growing. You get some sort of, collection of things later on. And as I said, as we've been saying, it's a Gaussian, so kind of a boring thing, but magnificent. Okay. All right, so lots of other weirdness. So that's a really good fundamental thing. Lots of other crazy things come out of random walks. So let's define C here of R of t. It's probably that after t time steps, a random walk, so our drunkard, has come back to the origin r times. Right? They've come back to the pub r times. And so think of our example where we had those examples I showed you, realizations of a random walk process. Let's have 10,000 of them. So if you're behind early on, what's the chance you come back? So imagine now it's a game, right? So you win if there are more heads, and the opposition wins if they have more tails. Flipping, right? So if you're ahead early on, is that good? Or what's the chance that you will win or lose from there, or if you're behind? A little bit deceptive what I'm going to say, but the most likely number of lead changes, right? So the most likely number of times that you change the lead is actually 0. So that's really bad, right? So if someone gets out in front, the most likely number, where someone has to start off in front straight away, right? But after 10,000, the most likely number of lead changes is 0. And in fact, so the probability that you've come back 0 times is actually greater than the probability you come back 1, probably you come back 2 times. Now you have to sum them up, right? So you could say versus the number of lead changes is 0 versus at least one lead change, and that's going to be different. But this is a very, very surprising thing. Now, here's where it gets super weird. So let me say it like this: so you're tied. You start off at equal. Any point in the future you come back to a tie. The expected time. So, and of course, the next coin flip, you move away from that tie. The expected time that you have to wait until you will be a tie again is infinity. Even though, right? So, say you flip a coin, it's heads. There's a 50-50 chance that you flip a tail, and you're back to where you are, right? So there's a good chance that you'll be back. It's just that the chance you'll be back after 4 steps, 6 steps, 8 steps decays so so much that you end up with it decays in such a way, right? In such a way that there's a chance that the first time you will come back is 10,000, 20,000, 100,000, a million. Those chances are non-zero, and it adds up such that the average time that you expect to wait for this game to be tied again is infinity. The average time you expect for your drunkard friend to come back is infinity. They will come back. Probability 1, they will come back. So this is really weird, and it's just coming straight out of random walks. All right, so it's good to start with simple things and not jump into the craziness too early, because it's craziness straight away. All right, so Feller is in here as well. I mentioned before. Okay. All right, so I've expressed this. So we'll talk about probably a first return, right? So this is a probability that our random walker comes back after 2 n time steps, right? So it has to be an even number. All right, and one could ask about higher dimensions. We're talking about our little random walker on 1 dimension, so we could make a 2-dimensional thing, and now they're allowed to go in any of 4 directions. 3 dimensions, they're allowed to go in any of 6 directions. And what's probably that they come back? So you can see it's going to get harder as you go up into higher and higher dimensions, because there are more ways to escape, right? And it's exactly how it's phrased. We talk about escape. It's a famous math problem. So it turns out in 2 dimensions. Well, I'll tell you later on, but it turns out that early on in dimensions, you get a change, right? So that there's a chance of escape. Doesn't matter what dimensions are. There's always a chance you come back. You just walk away and come back on the first time step. So we know trivially that there's always some non-zero chance of coming back, but it disappears. Okay, so why do we care? Because, well, I'm giving you this as a nice example of finding a power law size distribution, seemingly for free. There are some physical structures that certainly have random walk structures, perhaps. And we'll, as I mentioned earlier on, we'll start to see how scaling relations work. All right? Okay, so that is kind of a setup. There's a little shout out to community there, community fans. Let's set this thing up then. Okay. So we have our random walk. This is the same kind of structure I've been showing you. So time is across the bottom, 20 time steps here. X, the displacement is measured on the y-axis. It's ridiculous we call it X and Y, but on the vertical axis. And so we know a return can only happen when we have an even number, and there's a return here after 8 time steps, one after 10 time steps, and then one after 14 time steps. All right. Okay. So the probability that we'll call this probably P little fr. That's going to be the probability of first return at t. And of course, as I said, it has to be even. So 2n time steps. Probability in counting, pretty much always connectable. Then we have all this nice stuff from combinatorics and stat mech. From physics, lots and lots of counting. Of course, we can go crazy. In many ways, lots of science is essentially advanced counting. Okay, so we're going to, this is a hard problem, right? So it turns out this is a hard problem. So what's the probability that we return for the first time after 2n time steps? Turns out that's kind of a hard thing to just write down. We'll do something sneaky, right? This is what we always like to do with these counting problems, is come up with something sneaky. So we're going to turn it into an easier problem. So let's imagine that our drunkard first goes to into positive territory, and in this case returns at time t equals 16. So let's see what happens with this kind of walk. So this, right, first return is at t equals 16. So they cannot come back. All right, they can come back to 1 as much as they want. So we're happy with all of these. So the question is, how many different kinds of walks do this? Let's think about this one first, and then we'll see how it relates back to our first return. So they're allowed to come back to 1 as long as they don't move below that, right? So that's our red line. So it has to be equal to or above. So we can think, all right, so now we can think of walks that return to 1. So let's imagine we start at 1 and end at 1. So we're going to take a smaller, we're going to get rid of the first step and the last step. And so we're allowed to have these kinds of walks. They're allowed, so now this is a bit easier. Now they're able to return, and in this case, after 14 time steps, they come back to the origin. All right, so we can phrase it like this. The probability that we have a first return at 2n time steps is the probability that, well, buried in here, so that we need that x of t is greater than or equal to 1, right? That's this piece, between 1 and 2n minus 1, and that the first, it starts at 1, ends at 1. That's this little piece at the end. There is a half, because we're going to deal with the fact that this has to come back to the origin. Yeah, and then we'll have 2 because we could go either way, right? We could also have walks that stayed in the negative side and they come back. So, okay, fine. That's what these last lines say. Okay, good. All right, good. Right, so this may not seem like it's a better thing, but it is. So we're going to count numbers of walks again, which is what we did for getting to the binomial distribution, which got us to the Gaussian in your assignment. We'll turn it back into probability at the end, right? So counting is easier, for me at least. So we'll use this piece that we figured out before, NIJT. So it's the number of possible distinct walks between position I and position J, taking exactly t steps. So let's think about all the paths. Let's start at x equals 1. So this is all paths, right? Let's start at x equals 1 and end at x equals 1, right? So they could go back to the 0 and they could do all sorts of things that we don't want. Let's just think of all the paths that do that. So if we could take all of those and then subtract out the ones that hit 0, right, then we would be able to compute the ones that never go back to 0, right? So we can actually count very easily the numbers that start at 1 and end at 1, taking any path they want. What we then, so we're moving away from our original problem. Now this is another step. If we can find the ones that hit 0 and subtract them out, then we're set. All right, so we'll call these walks excluded walks, and we'll use what's called a method of images. It's done in lots of kind of problems to find them. So this is it's a sneaky thing, very sneaky thing. All right, so here's an example, couple of excluded walks. So the this guy here is a bad one, right? So the one in black's the one that starts at 1, ends at 1, so principle is good. And we see here it comes back to 1, that's fine, but it hits 0 here, so that's a bad thing. All right, so we want to get rid of this guy. We want to not count it. Here's another example, actually drops below 0. So here's the observation, as we say here, that as when we hit 0, we can take that first part of it and mirror it, right? So I've just reflected that about the origin. And then this blue path here, we're going to let it continue up and follow the original black one, right? So for every black curve that hits 0, we're going to do this. So here's another example. Here's a black curve, it hits 0. The first time it hits 0, we're going to take the whole trajectory beforehand, flip it, so it starts at -1, hits 0 here, and then we're going to let it run on the black curve after that. So this defines, so in both of these examples, we started at -1 and we're going to end at +1. So you can see that construction is always going to work. Again, -1, end at +1. And this identifies, so for every black curve, the black trajectory that hits the origin, right, hits 0, we can make one of these blue ones, and they're unique, right? So there's going to be, right, so these are the things I've said. Right, so we match the first part until it's 0. All right, so for every one of these black curves, there's a blue one, and for every blue one, there's a black one, right? So there is a 1-to-1 correspondence between these two things. So actually, we can say, well, let's count all of the guys that start at -1 and end at +1, and then from them, from those, we can see how they have to cross the origin, right? So we go back the other way, we take this blue guy and we flip the first part up until when it hits the origin to make this black curve. So again here, we'll take the first part, hits the origin for the first time, we flip that part and we make the black one. So this is a way of manufacturing the bad trajectories that start at +1, end at +1, and hit the origin at least once. All right, so, okay. So we have this identification, this 1-to-1 matching. So the number of, that's exactly what I just said. So the number of, I have to think about this, the number of first return walks after 2n time steps is equal to the number that start at 1, end at 1, take 2n minus 2 time steps to do so, minus those that start at -1, end at 1, and take the same number of time steps, right? Because these are all of the bad guys, the ones that start at 1, end at 1, but have hit 0. So what we've done is we've turned our problem into one that we can deal with, right? So we know you've computed these binomials, we can count those. Then we have to play with them a little bit to combine them. So we need to combine them into, right, so there's lots of factorials, we have to combine them into one blob divided by a blob. That's good. And then we can, and you will, play around with Stirling's approximation and some other good things again. And we will get the number of first returns to look like this, which is pretty great, right? So what's in here? So there's a 2 to the 2n minus 3 halves on top. Right, this is the thing that just comes out of that previous calculation. This is a number of them, so it's growing. Somehow we get a pi in there. Very good, root pi. And there's an n to the 3 halves. So that's the big deal. So there's this exponential growth on the top, right? Because we are getting more and more paths. Because this is not really conserved, right? So there is, yeah. Right, just a 2 to the 2n number of paths. Number of distinct paths after 2n time steps, right? So it's growing exponentially. All right, n to the 3 halves on bottom. So this is the term we're interested in. It's a minus 3 halves, which as we've talked about before is totally crazy, right? This is one where the mean is infinite, the variance is infinite, all higher moments are infinite for this, the probability distribution that rises out of this, and so let's get to our probability, but it's normalizable. So we have to normalize it. As I said, total number of paths is 2 to the 2n, so we divide through. right? Just it probably comes out of this. So we're dividing through by 2 to the 2n. And now, and I'm just sticking this guy back in here. So we're going to, these two cancel. Yep, they go away. And the minus 3 halves, this 2 to the minus 3 halves can be combined with this end of the 3 halves here. So there's a 2n to the minus 3 halves. Great. And a 1 over root 2 pi at the front. Really beautiful. Actually, I had this on my webpage for a long time as a little symbol, because it's just great. So it's proportional to t to the minus 3 halves. Because 2n is t, right? We had an even number of time steps. And there it is, all right? So probably the first return after t time steps is decaying like t to the minus 3 halves, providing we're talking about an even number of steps. All right, so some of these things I just said. So gamma, we've been calling this exponent gamma. Gamma is 3 halves. It's the same thing if we had continuous space-time walks, right? There's all sorts of ways to think about randomness that are not about this. You know, we don't have to frame it in this discrete way. We talk about Wiener processes and so on. That's Norbert Wiener, not Anthony Wiener. Very different processes. Okay, so yep, and let's see. So it's normalizable because it's not. Gamma is greater than 1. The term that's used is recurrence. Means that our random walker, our drunkard, will always come back to the pub, but all the higher moments are infinite, which is craziness, right? Hashtag total madness. So even though our friend will come back, we expect to wait. You should expect to wait a very, very long time. It's bad. So one moral is don't get drunk. Don't be the drunkard, which hopefully you would have picked up by now. Another one is if you're gambling against someone who's infinitely wealthy, right? They can go into a deep enough well, then you're in trouble because, you know, it's a fair game. Then you're in a lot of trouble because eventually it will come back. Eventually, even if you're in front, it'll come back. But you could wait a long time, and you will run out of money because you don't have infinite time and infinite money. Infinite time is the real problem, actually. So let's see. Must work on immortality. All right, so higher dimensions, it turns out, and this is all quite beautiful, in d equals 2, the walker always comes back, right? Mean, of course, will be, you know, infinite as well. I mean, you can see it's even worse. But there's a probability for d greater than or equals 3 that our walker will not come back. Okay, so this is, you know, beautiful results. You know, about 100 years ago, this was figured out. And you can enjoy this. This should be a nice wiki. So it's right there. You go. These are all the great constants. So this is it's great. So the probability of returning is 1 for dimension 1 and 2. It's smaller than 1 for higher dimensions. Probably in 3 dimensions is this joyousness here. So it's about a third, right? Third of a chance of coming back. This quantity here is 1 minus 1 over u3, so this quantity, really fantastic, is this thing. Yeah. So you can see that's maybe trickier to work out. We're not going to do it, but great problem if you want to. And then in d dimensions, you have that same form, and it just keeps going. So there's a nice generalization. Yep. So much joy. Let's see how our friends are going over here. That's the slow one. This is the one that was faster. Oh, it's kind of caught up, has it? Yeah. Go faster, go faster. All right. It's making a nice normal distribution. All right. Lots of little Easter eggs, I hope. So on a finite space, you have a very different thing, right? So the random walker actually will visit every site with equal probability. This is a invariant density. There are other terms for it, but invariant density is, as in probability density, it's what's the long-term spatial probability distribution for where something may be located, right, in a system, in a dynamical system. And so, and of course, in chaotic systems, it's when we get these so-called strange attractors, these invariant densities that are non-trivial and often beautiful. But in a finite space, yeah, you're going to, there's a very important thing, it's diffusion, everything ends up being flat. Really nice property is on, occurs on networks, and we'll have a little bit more to say about this in the complex networks section of the course later on, and then also in the following course, complex networks, of course, we'll dig into this as well. What you find out there is, and I'll just tell you about it here. So a random walker wandering around on a network, any kind of network, but let's just imagine there's nothing special about the links or nodes. Once the walker reaches a node, if there are k links, k places to go after that, then they just choose with probably 1 over k where to go. So we let our walker wander around, and we have many, many walkers that don't interact with each other, and we let them wander around. What you see is they start to cluster on nodes with higher and higher degree, disproportionately, and in fact proportional to the degree. So the degree is the number of friends or edges, however you want to put it, for a node in a network, right? So the number of connections a node has. We have to come to that. So that's very, very nice, right? There's Google's original stories connected into this, right? Because you're wandering around a network trying to find where things end up. We've moved away, so there's a really beautiful thing here. We've moved away in finite spaces. The nodes, the walker would be, right? You have this nice little, say, a little grid. Then your walker is, well, even there it's a bit tricky. Even there you get some edge effects, of course, it's true. What you start to see is that what you realize is that it's actually the edges on which the walkers are equally distributed, right? So if you forget about the nodes, now look at the edges, and you look at the traffic on the edges of all of these little walkers, you see that each edge is being traveled by the same abundance of walkers either way. So that's where we get that's where we see the deeper kind of piece of diffusion is that's where this uniform distribution manifests itself properly, right? So the actual spatial locations will be unevenly represented, but it's in the trajectories. All right. Okay, so the next piece is going to be about example usage of random walks. And there'll be a break probably in what I'm recording here. Okay, so let's do that. Let's get on with that. So this is a problem that I came across a long time ago, my PhD, and so it has some nice, it's a nice example application. So-called Scheidegger networks, this is from the 60s. Just a simple way of thinking about random networks, random kinds of river networks. So imagine you have flow, right? So this flow is going to go down through these paths here. So you can imagine water falling down or droplets falling down the window if it's raining, or a very steep slope perhaps. And really, there's a triangular lattice under here. So so you realize that the lattice by giving each direction a plus or minus 1. Okay, so it's a triangular lattice. We're going to, and here's a very big example here. So flip a coin, and then you draw a line, depending if it's left or right, and then you make a network. And so what's going to happen is you get these, you can think about this, you'll get random walks in the blank spaces, right, in the so-called divides between basins. Right, so these are random walks. So the boundaries of the basins will be random walks. And it turns out, in general, they are, I'll come to this later on, there are more fractional random walks. You can think about them like that. So we work with random walks to start with, and then we go into fractional ones, and they have much more interesting complications. But so here's a simple model. And one thing about real basins is, well, there are basins of real river networks, and we're talking about continental scale ones, everything up to continental scale ones, they have shapes to them, and one would wonder, you know, are small basins like big basins? This is something we'll return to at the end of the course. Right, these patterns are beautiful. I mean, if you've ever flown across them or just looked at a picture taken from even a satellite, but from planes, then, you know, beautiful fractal patterns that appear through erosion, right? So what's describing these things? Okay, so this process creates basins with random walk boundaries, and we see that if you really, what those walks are like is that they're not quite what we had before. These walks are moving left or right with probably 1/4, and then they're staying in the middle with probably 0, right? So it could be that the basin didn't move. Okay, that can happen with half a chance. So basically, it's a random walk, though, with probabilistic pauses. And well, let me do it here. I guess this is the way to do it. So imagine we make our two random walks like this, and they hit each other eventually at some point. Maybe they hit like this. So here's our random basin. So you can subtract one from the other. Right, so let's call this, this is now really, you know, X and Y kind of thing. Right? It's a spatial story. So we'll call this you know, F1 and F2. And then if we subtract one from the other, we get some kind of walk. This is what I was trying to say, F1 minus F2. And it's a slightly different business in that in here you can have them staying or staying maybe, right, with probability 1/2, and then moving down. So it has periods of stases in it. So it's a random walk, but just with probably a half, it doesn't do anything. With probably a half, it behaves like a normal random walk. With probably 1/2, it just carries on. All right, so So it then becomes, so this is a first return problem, right? So it's a first return. Right. What's the length? So we'll talk about the length of this basin, L, and we'll talk about its typical width, right? So we might call this, we could call it L parallel, so it's parallel with the basin, and we'd have something like L perpendicular, right? That's a typical width here. Now, we've figured out this thing about first returns, so we know the probability. So if we take all the basins in this great big landscape, the probability that a basin has a length L is going to be proportional to L to the minus 3/2. So, and that's true actually in real river networks. It's not the same exponent, but in real basins, in real landscapes, you see this. So this is, you know, very tantalizing. The number is slightly different, and I'll show you what that is. But let's connect it with some other pieces, and we have some very simple things we can do. So for example, we know from our standard deviation calculation for the variance of a random walk that the typical width is L to the half, right? So these basins will have a typical width of L to the half. And basin area then is just this length times typical width, so L times L to the half. This is just a little back of the envelope scaling computation. So we get L to the 3/2. So this is area is proportional to that. If we invert this, we get L is proportional to A to the 2/3. And from this expression, now we can compute a probability for area, right? So we probability of length, if we pick a random basin, is proportional to L to the minus 3/2. Now what's the probability that its area is something? It's not as simple as just replacing A with L to the L with A to the 2/3. We have to be careful with the probability distribution, so we need to look at the DL part as well. So DL is going to be d a to the 2/3 proportional to it. So we're just sticking a to the 2/3 in here. This is a simple derivative, right? So we get, differentiate that, we get 2/3 a to the minus the third, right? We're just taking one off there, dA. So these differentials can be replaced. So the probability of basin area equaling a dA, right? We have to have the dA and the dL in there if we're doing transformation of variables. This will come back later on when we look more generally at variable transformation for probably for our power law size distributions. So this has to be equal to the probability that a basin has a length L, dL, right? Those things have to be connected because we have a relationship between A and L. So we can put those guys in there. We have L to the minus 3/2 dL. And so we replace each piece. We'll replace this little, oh, this is much nicer. We'll replace the L to the L with a to the 2/3. So that's this piece here. And then it's to the power of minus 3/2. Now there's an a to the minus 1/3 dA appearing from the dL. So these guys cancel themselves out, and we end up with a to the minus 1, right? These balance. A to the minus 1, a to the minus a third, so it's a to the minus 4/3. So that was not entirely obvious that that would happen. And in general, we'll call that exponent tau. So we pick a random basin, like a nice closed basin, out of the landscape. Probably that we have a length L is proportional to L to the minus 3/2, and we have an a to the minus 4/3 for area. So they're both pretty bad exponents, right? This isn't far away from 1. Minus 4/3 is not far away from minus 1. So that is a very much distributions of surprise. And again, these are not exactly what you see in the real world, but they are not they're not far off it, and they give the kind of right flavor. Okay, so good. We have these connections. We want to connect these exponents now in a more general way. So we've introduced gamma, which is just what it's called in that also what it's called in the literature generally for river networks, and tau. We have this new exponent tau. So these are called scaling relations we're going for now, right? What's the relationship between tau and gamma in general? Something that happens in many, many different systems. We have different power law size distributions for different aspects of the system. We should be able to connect the exponents together. So you usually see this if you have a big enough network to work with. You know, it's difficult stuff, of course, but the data that I used to play with in my PhD was mile resolution of continents or kilometer resolution of continents. Of course, it's much better now. I still think I think we still might have better resolution of Mars, but there you go. No atmosphere and trees, you know. All right, so this is typically what people see, and we're going to generalize this relationship between area and length. So before we had length is proportional to a to the 2/3, and that's known as Hack's law, actually. So Hack's work was in the late 50s. It was for a small basin. Notice that for a small landscape, the basins in there had this relationship where actually it's the length of the main stream in the basin was scaling as a to the h, and that's a more complicated thing we can deal with, but as area to the h. And he found it was kind of close to 0.6, all right? So we will see this later on. Large networks, it's actually about 0.5, which makes sense, right? If length is meters and area is meters squared, then power of a half makes sense. It's a normal, boring kind of scaling. It's possible for smaller basins it's greater than a half. This is a bit exciting because it's hard to understand why that would be. We'll call this allometric scaling later on. The first one is an example of isometric scaling where h is a half, it's isometric. Little basins look like big basins. Allometric ones, then you'd have to stretch them in different ways to make them little ones look like the big ones. There are certainly models with very with non-trivial values of h, and I just showed you one where we have h is 2/3. So let's redo this calculation with gamma, tau, and h. This is a very standard thing. We're trying to find scaling relations. So we're going to have these three pieces. These are our three ingredients. This is a relationship between length and area. Is L is proportional to a to the h. We'll call this the hack exponent, this little h. Area is proportional to area to the minus tau, and length is probably for that, I should say, and probably for length is proportional to length to the minus gamma. All right, good. So then we have exactly the same thing we did before. So we connect the differentials. So dl, we just put a to the h in there. It's proportional. Take that derivative. We get h, a to the h, dA minus 1 dA. So this is the big deal. So let's do exactly what we did before. Let's connect tau into to gamma and h. Same structure. Probability of basin area of A dA, probability of basin length equals L dL. These guys have to be the same because we have a nice connection between them. We know this, it's L to the minus gamma dL, and we're going to replace the L and the dL with the ingredients we just created. So we have an A to the H for L, that's the hack expression, and we get an A to the H minus 1 here. All right, so that minus gamma is going to change things, and we end up with A to the minus 1 coming from here. There's a minus, there are a couple of h's, so we'll put them together. So we get, and there's a minus sign out here, so it's going to be plus h gamma minus 1. All right, so that will give us a plus h back here. That's this piece. And there's a minus gamma h. All right, so this has to be a to the minus tau. So we have tau is all of this blob here. So tau is 1 plus h gamma minus 1. So this is what we would call a scaling, what's called in physics a scaling relation. Not just in physics, but originally called in physics a scaling relation, but we see this for all sorts of things. Cities, for example, lots of different scalings, whatever it is, crime and innovation rates, you might find them there. You might find them to do with energy usage in ecology and biology for different kinds of organisms and all sorts of other aspects. So if you have a system that has lots of different power laws in it, and some of these are probabilities, and this one is a relationship, then they should be connected in some way. So it turns out you can go a little further, and this is fine, but you can go a little further. There's actually, this collapses a little bit, so tau is 2 minus h. This is actually some work that I did. Gamma is 1 over h. So that works, let's see, so that works nicely for the example of random networks, these random river networks, so directed ones. H is 2/3, we ended up with 4/3, that's correct, and H is 2/3, we got 3/2, so that's good. But you expect, and you do see this for real networks, even when the tau and gamma and H are not what you get out of models, they do have this nice connection. So one extra thing here is then you can see that you really only need H, right? So that simplifies the description of the system, very important thing. So this is a very important thing for complex systems. As I said, you expect to find these scaling relations. If we're trying to model this, then of course we can focus on what we deem to be the kind of core exponent, right? So this is a connection between area and length in this case. That's the thing we might focus on. When we talk about universality, maybe this h equals 2/3. Well, we've seen it; it's a special class. Maybe there's h equals a half. Maybe there's h equals 4/7. Maybe that's producible by a model. Maybe there aren't any in between. This is something we're going to come back to for rich gets richer models when we're thinking about other ways of generating power laws. When we get to networks, the way networks become bigger networks. There are some systems where there are only really few discrete separated kinds of scalings and therefore forms of the whole system. And there are some where it's tunable and it depends. And so we'll see how that works out. But that's our story of universality, right? So we'll get there. So It may be that the classes of real networks, these kind of erosion type networks, there are only a few different classes, and that depending on the kind of overall system, you could either fit into one of 7 or 4. That's a great thing to find out. We haven't found that out yet, I don't think, for this example. But to characterize it, then you just have to go and measure the one exponent. You'd measure all the others, but there's one that you go to first. So just a couple of other examples. Here's a fun little piece. So you can imagine a simple failure kind of model, right? So the health of the system is going up and down randomly. You have to use really simple models to start with, right? So this is not a whole model, but a kind of a basic model. You start with some initial health, and the entity will fail when x hits 0. We know we'll get there, unfortunately, but that again can take a long time. Different kind of probability distribution associated with that. It also appears in streams. I'm focusing a little, I guess, on geomorphology because I worked on it, but this is super important stuff, right? So you have bad things or good things being deposited into streams, and you end up with these. You can have kind of random walks for how long they're entrained in the flow, and then they hit the ground and get stuck for a while, or sort of the bottom of the stream. You can imagine them being picked up again. And so you get that kind of description gives you a sense of why you might end up with very long times for things to clear out. Again, power law size distributions. Okay, we can generalize random walks fantastically. A lot of beautiful work, and I've got all these links for you here if you want to get into it. We talk about levy flights, fractional Brownian motion, fractional random walks. There's a lovely piece of work from 1982. Distributions with long tails, right? Power law size distributions. The 1D version of it is to say, and this will be useful potentially later, is to talk about the standard deviation. So for random walks, for Brownian motion, we get t to the half, and we call it diffusive. It's diffusion. If it's greater than a half, we call it super diffusive, right? So it's the width of the distribution is growing faster than a normal diffusive one, so it's super diffusive. Sub-diffusive if it's less than a half. It turns out there's not a simple mechanism. So random walks, very simple to generate, right? Plus or minus ones. If you want to get to these levy flights, and they give you super diffusivity or sub-diffusivity, then you need to, the path needs to, the next movement has to depend on the path that's come before, right? So integrals appear, and it's more complicated, right? So memory matters, which is fine. Memory is very important. All right, so that's a good place to stop for now. The next section is variable transformation. I'm sure you were psyched about it. But this is all a very nice setup for some problems that will come later on. Variable transformation will matter again. But random walks, really, really nice things. It's good to know that just out of just pure simple randomness, you get very interesting, complicated structures. The universe, for example. But that is a good place to stop. Okay.